Okay, so let's see, to begin with, we can try to do this, just say about this Lagrange interpolation. Yeah, this is apparently important. So, second, yeah. And the very idea is to determine a function with some information given. You want to determine the entire function. You want to determine the complete function. Okay, maybe that's, let's just say polynomial. Yeah. That's on one level, that is what it is, though there are better ways to say it. So what you're trying to do is determine a polynomial given a complete set of information. Set of information. So just to make us think in a little broader way, can you guys tell me what would constitute a complete set of information? Let us say this is n degree. So I'm asking if you can expand on this complete set of information. At n points. Yeah. So you would you should need values at n plus 1 points. Is that right? Or yeah, let's just say n plus 1 points. Okay. I mean, if you say that it is yeah, still you will need values at n plus 1 points. Yeah. So values at n plus 1 points. So will knowing values at n points be enough in any case? This is one kind of complete set of information. So if I tell you that your polynomial is monic, in that case, is knowing it at n points enough? Just to think, if monic is given to you, then so this is just thinking, right? Are endpoints enough? Yeah. Okay, Raghav, what do you think? Right. That's a good way to think, right? Just simply for a linear, if it's x plus c, then just knowing it at some value at some any point is enough. And so in general, knowing it, if it's a 3 degree, or let's say 3 degree polynomial, and because there is just 3 coefficients in that case, which you have to find. If it's given to you that it is monic, right? But again, there are some subtle things here. You cannot just assume in the problem that it's monic. No, such things work when you have to work with the roots. The roots and all don't change, but the polynomial changes. If you assume it's monic, then it becomes a different polynomial than maybe what was intended, right? And if you have to take sum of two such polynomials, then everything might change. Okay, so you have to see carefully what is given and what you can assume. And so, but yeah, in this case, the endpoints are enough. So just to say this thing, because not every time you need all the n plus 1 points, and just to think about this, I have said. So, okay, so this is how we will think. Fine. So this is, I mean, this is what we were going to discuss, values at n plus 1 points. Cool. But is there any other set? Because in more disguised ways, or in more with the same theme, if questions, come, or we want to see, is this part of a more general philosophy? What something else, some other piece of information that would completely tell you the polynomial? Well, obviously, one thing which all of us like is almost a definition, is the all the coefficients. But let me write that. Okay, I'm trying to say that none of these are special. Okay, all the coefficients, that is certainly there, right? Anything else? Yes, I'm saying that like if all the coefficients are given to you, then the polynomial is given, right? That's another, that will be C, right? So these are some obvious ones. But all roots and another point or a leading coefficient, yeah, all roots plus one more bit of information. But that's fine. These are okay. So I'm trying to say that all of these are equally good in the sense that they are equally generic in some sense. Okay. Or let me not. So is there any other which is different from these? Obviously, you can say all the roots plus one and so on, but something which is different that could be given to you, and that would also constitute a complete set of information, or let me say determining set. What else could be a determining set? What other piece of information could help you to find the complete polynomial or the complete function in many cases, in fact? I can think of one more. I'm trying to think if there are some other standard. Oh, see, n plus 1 points is pretty standard. Yeah, that already captures a lot of things. Okay. Okay, something which is like calculus, coming from calculus. No, only f dash, no, it's a general n degree polynomial. So, but yeah, that's the direction maybe you can think, Rasubro, if you can think on that. Okay, no. That's okay. So if f dash x is given, that's okay. But yeah, if f dash x is given, but I'm kind of maybe a discrete, right, is what I'm maybe asking for. That's interpolation. So from discrete, we want to go to continuous. Discrete. But you're right, that's where it's coming from, kind of from derivatives. Taylor's theorem, something like that. So just knowing all the derivatives at a certain point is enough, right? I find this to be very remarkable, right? This is indeed something to be thought of. It definitely works. Any point, it could be, so let me not say one, right? Do you guys agree? That if all the derivatives, well, up till n, and in fact, the degree will also be determined maybe, yeah, from here. But let's see this. This is also a complete set, complete information set. Is it? Yeah, are you guys agreeing on this? Yeah, right. And in fact, well, this one is very similar to C or maybe to B, right? Very similar. Can you guys say how it is similar? B and D are very similar. Yeah, so you can think about that later. This is simple. Okay, so now we really want to say how that information is determined, right? Or rather we'll focus on point A and try to see how it is determined, and maybe we can, I don't have any examples that much in many problems at hand right now, but you can see. But before going forward, I can maybe also say here that what we are really trying to do is we are trying to miss another way to look at Lagrange interpolation, which is also very so like this thing about Lagrange interpolation, that, or this way to see it, that you're trying to determine the polynomial using some set of information. This theme you see comes in Taylor's theorem and roots and so on, right? And so that's one way to determine. That's one way to determine polynomial. Lagrange interpolation is one way to determine polynomials. But another way to see Lagrange interpolation is basically writing a polynomial. Yeah, writing a polynomial using a special, or rather using special polynomials, right? This I will expand once we have the formula. Okay. So writing a polynomial. This also answers a lot of questions. Okay. Writing a polynomial with maybe using special polynomials. Yeah. Well, one thing is that, I mean, everything that you write, when you write any polynomial, what are you doing? You're writing this polynomial using some special polynomials, right? Using x cube, x square, x, and the constant polynomial, maybe 1, right? And when you're writing a polynomial with using these polynomials, then you're getting these coefficients. Maybe they're not so good coefficients. But how about if you wrote this polynomial using some other polynomials, right? Maybe if you wrote it, I don't know, and you have to really think sometimes with what basis you want to write, with what number base you write a number, and some things about the problem you get some pattern, because the digits start having some pattern when you change the basis. In the same way, polynomial may be very bad random, right? But when you write it using some other basis, using some other, so let me not use the word basis, using some other set of polynomials instead of these standard ones, x square, right? Then the coefficients might become simple. They might have some pattern, right? And so you can also obviously write this polynomial, and this is also very, this is not what Lagrange interpolation does. It does this, but not using this type of polynomials, using some other, but we will see that after we have the formula. I think that will be better. But do you guys agree that you can write a polynomial using these polynomials, x minus 1 cube, x minus 1 square, x minus 1, and x minus 1 to the power 0? And right, so can we, do you guys know how to do this in a systematic fashion? Because apparently this is important. So I mean, so we know it can be done, but do you know how to do this in a systematic fashion? Yeah, but that is not, yeah, that's okay. Expanding and is comparing is okay, but in a better way, is there a, yeah? Yeah, why is it not good? I don't know. But yeah, more, yeah, let's see. No. It's the same polynomial, right? It's not a different polynomial. Yeah, so there is a much easier way than expanding that. That's the little cost that you can see, right? You expand and then um, so you're saying x equals to y plus 1 like this, and uh, um, but won't it change the polynomial, right? Yeah, but there's the most standard way. Like, how do you do basis change in numbers? Try to use that idea, right? Instead of base 9, you're writing it in base 8. How would you do it? Yeah. So, well, this is known, right? You divide px. Yes, you divide px by what? You divide px by x minus 1. Oh, right. And then you have a remainder. Maybe this is just a number. And this is the coefficient, right? And again, you do the same thing for p1x. Iterate, right? And in this way, and this has a lot of significance. Like, this is very, very important. Okay. So this is what we are doing here is basically we are writing a polynomial which is in a certain, with respect to a certain basis, and we're changing the basis. And with that, obviously, the coordinates, right? These coefficients are like coordinates. They also change. And that's, yeah. So this is also Lagrange, this is like Lagrange interpolation is also something like this. So it's two things in that way. Okay. But let's now come to the, yeah, more concretely what Lagrange interpolation. And let's keep these two themes here. And we'll try to see if we can use them. And later on, one can also ask what special polynomials are can we use to write any polynomial? Let's say a degree n. And when is such a set special? That's also a very good question. So anyways, so let's come concretely. So what are we given in the Lagrange interpolation? There are many kinds of interpolations, right? So in Lagrange interpolation specifically, what is the information that is given? So we are told that given px is, well, this should not say degree n, and then some n arbitrary or n plus 1 arbitrary points are given to you. So let's not say a, let's say use x, right? x1, or let's say from x naught, so x naught, x1, x2, and so on. And so these are n plus 1 points. These are fixed points, right? These are given. So let's just be very clear. So these are fixed. Yeah, but they're arbitrary. So what we will prove will work for any. Okay. And then we are told the value at these points. Yeah, these are also given. And then we want to, maybe I should just say we want to find the value of p at any random point. Find p is one way to say, but really we don't find p in the traditional way. Means what we get in the end is not p in the traditional sense. Okay, but maybe I just say, yeah, find p of X for arbitrary X. Yeah, this is what we would want to say, like what value will P take for an arbitrary X. Okay. Right. So how is it that we do? Obviously, there is a formula, but see, I don't want to look at the formula directly because I never remember it. Okay. And but there is a way in which, given this thing, you can just think systematically from very small ideas. Is, well, you can think of it like this: that P is something. This is the way I think. I mean, P is something that so P is a polynomial, right? And P is something that at the point x naught, it takes a value Px naught, right? So at the point x naught, it takes a value Px naught. So you create a counter for x naught, right? And similarly, maybe you can create a counter for x1. Yeah. And you create a counter for x2. And so on. Okay. Yes, and many times, even a few years back, CMI problem was this interpolation, but it was like a Taylor's kind of interpolation. Okay, so yeah. Yes, it's very important. And also these are if you understand things properly, then you can use these things to study more, like linear algebra and so on, comes out of these things in a very nice way. Yeah. It's a very, so, huh. Yes, right. So that is, yeah, that is the formula. I know. So that's the formula. I'm just trying to tell you this is the way I think. I mean, all of us know the formula, it is there, and if you know it works. But but I have to say something. So I'm just trying to say it in a certain way that, well, maybe you can think about it like that. Okay. Like if in case you forget, hopefully you won't. But yeah. So I just, my way to say it, well, this is the thing. The way I think about it is that now if you, when you put the x naught, then you get px naught. So these things are going to have to vanish, right? These other things are going to have to vanish. So how do you make them vanish in a natural way? Well, you just, there is no other natural way, right? This is the natural way to make them vanish is like this, right? And similarly, when you put x1, yeah, then also, then what do you want? You want the first and the third to vanish. Maybe I shouldn't be saying this. This is maybe some for kids. If I can say them, then it's fine. But still, I'm just saying, okay. Then x minus 1, right? Yeah. And similarly, for x2, you want to the first one and the second one to vanish. Yeah. But then again, there is a normalization which you have to do, right? Because now when you put p of when you put x naught, then these things vanish is fine. But when you put x naught, then you get x naught minus x1 and x naught minus x2, this extra thing, and so you have to divide by that. And these are distinct points, obviously. And so you see, I'm just saying that this is just a natural way, and surprisingly, this is never said like this, strangely. But I think this is just one doesn't have to then try to. It's a basic idea from the points you are. And so x1 minus x naught and x1. Like I'm just saying that it's a very natural construction, and so when something is happening naturally, then you can expect other good things to happen from there. Okay. This is the standard formula. Okay. So certainly it's a complete set of information, and that we knew either way. Kind of, we know that otherwise also. But how does this fit into the second thing that I was trying to say? What are the special polynomials with respect to which we are writing Px? Yeah. Let's just keep 3 points. Doesn't really matter. What are the special polynomials that maybe I was trying to say earlier? You can see that now we are writing Px with respect to different coordinates. And what are those coordinates? There is this polynomial. I mean, not what are the coordinates, I should say, we're using the special polynomials. This is the basis, but this is different. So we're not writing, we have not got Px in the standard way using the powers of x in terms of powers of x. Like we don't have the coefficients of Px in the high school language, right? If you want to say. But the, no, that is right. That is right. Expanding is okay. But yeah, that certainly is correct. That is, yeah, you can go from one form to the other form always. But the point I'm trying to make is that, see, you're determining Px using these special polynomials. Yeah, is it right? So this is what I was trying to say, that given, let's say we are in the 3-degree world, right? Then given any 3 points, or no, so 2-degree world is a 2-degree, sorry. Yeah, given quadratics, so n degree n plus 1 points. So let me just say in n degree. So given degree n polynomial, right? And then given any n plus 1 points, given any n plus 1 points, given any n plus 1 points, this is already given. These, maybe I should say, any Px, any Px, okay, can be written uniquely as linear combinations of basically, maybe I'll just say x minus xi hat, which just means that in the product x minus xi is not present. Okay, so you understand that, right? Okay. And this is a very, I mean, if this question is asked to you, maybe you will not think in terms of interpolation, but this is the same question as interpolation. Do you guys agree? Yeah, this can be a question tomorrow, right? It is a straightforward thing, but yeah, given any, so given any n plus 1 point, so maybe they just say that given these polynomials, or rather just they are here, right here, given these polynomials, and you can look at how they are special. Yeah, they are not just any arbitrary. Yeah, so the points are fixed and one factor is missing from each. And they can be used to generate any polynomial. Yeah, because these are just some numbers. And that theorem we have proved here. And in fact, we have proved more. I mean, in fact, Lagrange interpolation tells you more. It tells you how that polynomial, what the coefficients, what the coordinates will be. Yeah. So is it fine? Okay. So then that is what it is. But then you see, so in one of the tests, I think last test only, we had this question. So I think you can guess now that if P of Q is in Q, then coefficients are rational. So do you guys see now this question can be done in a very smooth way by Lagrange interpolation. So in fact, that question was Lagrange interpolation. So just tell me how. So just try to see it. You can take any endpoints. Yeah. Mm-hmm. I mean, so you can assume the degree is n for px. Let's say degree is n. Points are rational. Yeah, because after you expand, the coefficients will also be. Now that's important, right? Because just saying that the coefficients in this expression will be rational is not enough. You have to say that after the expansion is done, then also the coefficients will be rational. Yeah, and in this expansion, you can say everything is rational. So, right. So then this problem becomes, I mean, we did it anyways, but yeah. No, there are some standard questions. Let me just maybe use one question. If you guys have any good questions, you can say. I used to have, I mean, I had, but I don't really remember. Just give me 1 minute. I had one question. Yeah, got it. Here. Uh, hmm. So let's just clean the board and example. So this is just a very example, but there are many good problems. Okay, I have to open some PDFs I have, but let's just do this problem and you can guys can do. Yeah, fx. Then you can ask me if you get stuck at anything. I'll try. So this is a quintic polynomial. So what is quintic? Quadratic, cubic, quartic. Quintic should be 5 degree, right? Just check. Quintic. Quintic is five. Yeah, right. Okay, so it's a quintic polynomial, and very interestingly, the f of 1 is 1, f of 2 are they? Yeah, 1, and then f of 3 is 2, 4 is 3. It's quintic, right? So it should be till 6. And find f of 7. So maybe you can use Lagrange interpolation, or there might be a shorter way. I don't know. Yes, anyone got? It's a, it's just you can try to use standard interpolation, or if you see some other pattern, try to see. Okay. So that must be right. So Rasubra, what did you get? Okay. Okay. Yeah, Rasubra, have you got anything? Oh, okay. So some 7. So what did you get? You got 8 again, right? Okay. So let's do it and check, right? So, but by the way, you can see that there is a pattern here, but that pattern is misleading. Okay. Can you see a pattern in these numbers? Yeah, but that is misleading because it's not said. Okay. So again, so Lagrange interpolation is also telling you that, I mean, any pattern, any finite pattern, you can put in a polynomial and make a polynomial out of it, right? Any finite pattern, you can make a polynomial out of it. Okay, where the pattern can be broken later. Okay. Uh, why? How can you put it? It will not be a polynomial, right? So that is the thing. So yeah, so you will get some strange. So you saying getting it. Let's just do it. So yeah, let's execute it. So if f is a polynomial, then fx is as usual, right? We write f of 1. So let's just write 1. Okay, so f of 1. And here you have x minus 2, 3, 5, 6. And so in the denominator, what do you have to do? 1 minus those things, right? So minus 1, minus 2, 3, 4, 5. So 5 factorial and minus 5 factorial, right? And f of 2 is also 1. So, I mean, just for illustration, we must do an example. So, um, so 2 minus 1 is 1, but 2 minus 3 is minus 1. Then there is 4, 5, 6. 4 factorial. Right. No, won't it be? Yeah, it won't be minus, right? Only 4 factorial. Right. And then this way, okay, so just please do it. Okay. Sorry. Yeah. Finish it. Okay, good. So, I mean, it's okay, fine. This is just a simple example. Good. Yeah. We can apply this interpolation idea uh, in other places, which is not really just interpolation. So maybe I can just say this idea of writing a polynomial with respect to special polynomials. Okay. So here is just, let me state it as a problem. And this problem also was something, it was we had said it as an offshoot of the one of the test problem, but this is an independent standard problem. And the problem is that, okay, so not really a problem. I should, yeah. So this is what we had seen. Okay, so uh, P of integers being in integers, that is, they're integer valued polynomials, valued polynomials. Okay, we had seen that it does not imply, and this was the problem we had seen, it does not imply that P of, it doesn't imply that the coefficients are integers. Now here coefficients, I'll say in a very careful way, because that's what we are going to play on. Coefficients with respect to the basis, when we are writing the polynomial in this usual way, this is with respect to the basis x square, because we have already seen, right, the coefficients will depend on how you write a polynomial with respect to what other, using what other polynomials. If you write it in the standard way, it doesn't imply that coefficients are integers. It does not imply. And we had seen examples, right? And then we have kind of agreed that the standard example is like this. So you can take x choose 2, right? You can take this, right? So I mean, obviously when you put in integers, it gives you integers, but its coefficients are not integers. So what do you mean by coefficients? When you write the usual sense of coefficients, yeah? Not integers. I think it's okay. That's the usual sense of integers, right? Of coefficients. And then also we obviously have this thing. These are all there, right? And in general, maybe let's write n plus 1 of them, because we are yeah, but let's just let me, just for completion purpose, I'm writing these two, though these two are not examples. Okay. Yeah, because this will be a standard way to do things. Yeah, but these last n minus 2 are your examples, right? So these are the polynomials. When you expand them, and you can see that when you expand them, the coefficients, I'm not asking you to expand them. I'm very bad to expand. But when you expand them, you can see that the coefficients are not rational, are not integers. Okay? But also, now this seems to be like a complete set. Seems to be. Do you guys agree that this seems to be a complete set of information for Px? Once again, is that any polynomial Px can be written using these polynomials? Yeah, I think you can roughly agree on that. Yeah. So let's do that first. Let's do that problem. Yeah. Any polynomial. So we'll see why I'm saying that. Okay. Why that problem is good. But let's solve this. That any Px, any degree n polynomial, y comma, any degree n polynomial can be written using these. Try to prove that. Again, you can say expand and compare, but then there is no guarantee that you will actually end up with an answer. right? So you have to say it in a way that, makes it clear that there is an answer, that it can actually be done. And for problems like these, you can look at Niven and Zuckerman binomial theorem chapter. You will get much more interesting problems. You solve and you should tell me sometimes. Ask me. Good for me also. So it is, so earlier we had something else. We had powers of a fixed thing, but now we have like, you know, these are called falling factorials. So you can just try to answer this question, and for that you can forget about the fact, because there those you can always yeah, it doesn't really matter. We are saying that any degree and polynomial can be written using these. So using these and some linear combination, between use the numbers multiplied with these and added, right? So you guys get the question, right? Yeah. So you are saying that, but don't think that given any n distinct polynomials that you can do it. No, even if they are not like multiples of each other, then also it may not be possible. But these are special polynomials which are looking. And there is a whole theory, the good problems can be made when some set is special even. And that's where matrices and determinants come in. But for this is this is just an explicitly. So you see what I'm asking, right? So there will be some coefficients, but not now. The next one will not be power x square, but it will be like a like this. You can imagine for some polynomial, this may be a better basis, right? If you're doing combinatorics, you don't know sometimes. See here. I mean, so earlier you would have just divided by x minus 1 repeatedly, right? But now you have to do something slightly different if you are going to go that. So there are, so think about substitution and do, this is just another kind of interpolation in that sense. or you can again think of division algorithm. So there are two ways maybe to do it. Okay. See, mathematics is all about writing something, picking some special vectors and writing your thing in terms of those, so that your coordinates are simple. Yeah, that is the whole point. Picking a convenient basis, picking a basis which is good for your situation, is what it's everything is about. Because that's how maths understands things, yeah, using numbers, and that means you need to pick the right basis so that the numbers you get, the coefficients you get, are something familiar, some familiar pattern is there maybe, that is, or some bound or something. So maths is all about, I mean, the more you do maths, you will see that this is obviously this is what it is, but in different ways. But this is what we try to do very often, picking the right coordinates. Yeah, I think that is what it is all about. In this algebra, decomposing things in a way. Picking special vectors. All those three x, y, z coordinates, they are not always the best coordinate system. That's why we have spherical coordinate system. This is like another coordinate system, not writing it using the powers of x, but using these. So, any ideas? You can just think about substitution, right? Substitution, why not? Well, I mean, you can imagine, I mean, how would you find C naught? Well, that is just P of 0. How would you find C1? P of 1 minus P of 0. And then you see C2. Right, it is extremely simple, right? You see, right, it's not difficult, right? And then this also tells you that in under what kind of situations you should consider this kind of basis, or consider writing it in this form. But you can also do it using division algorithm. Similarly, division algorithm you could also use. You can think how. I mean, so it's like in the first step you have to divide by x, but the next step you have to divide the quotient by x minus 1, right? And then further quotient by x minus 2, and so on, right? Then you will get an expression like this. So writing numbers using factorials. So these are standard things, right? I think this was also some ISI problem, right? Some factorials and writing proof that a number can be written using some factorials. That was there, yeah, right? So that was also basically like writing something using certain coordinates. Okay, so these are the ways. So this is simple, but now we are going to write these integer valued. What happens when you write integer valued polynomials using these coordinates? Or let me just mention uh, what happens when you write integer valued polynomials using these coordinates. Or no, so these coordinates, I'll just adjust that, I'll bring the factorials back. So these are the natural integer valued polynomials, these polynomials that we are looking at on the screen, right? Well, not these. These are integer valued, but these are not interesting in that sense. These are natural integer valued polynomials, and this is a large enough set apparently. What happens when you write an integer valued polynomial using these things? Now, what are the coefficients? What can you say about the coefficients? So when you write px using, so now px is integer valued. let me just write x choose 2. What can you say about the coefficients now? So earlier we saw the coefficients are not necessarily integers, but now if you somehow, when you write it like this, then can we say a pattern, or rather in this case, the property? Right, integers. So the coefficients are integers, right? And we have just said it. That is that's a good thing, right? That they are integers. I mean, this is not difficult, but if this is given as a problem, just did it, then it's a decent question, right? But because we have said then the stress, but either ways is. So this is the thing. Tomorrow you may see some other collection of polynomials with respect to which it can be written. And this is all that there is, mostly. It comes in different guises. There cannot be much other. Yeah, it is algebraically. Otherwise, it becomes a combinatorial problem or analysis problem. But algebraically, this is what there is. But now let us, I mean, since we have been talking about it, really the interesting question that should come is, I mean, what n polynomials form a complete set, or rather mixing the two things, right? Which n polynomials will give you all n degree polynomials? That is the question. Okay? That is really the question. Which, I mean, so far we have the sets, we have looked at a few sets like that, right? And like x, I mean, powers of x minus 1, powers of x minus anything. Then we saw that given any n plus 1 point, those products. Then we had these x choose i's, these. But in general, which set of n plus 1, yeah, n plus 1 polynomials, or rather which subset of n plus 1 of n plus 1 polynomials can, rather will give us all polynomials. And note that whatever we have done so far, the coefficients have been unique because we just had the right number of polynomials, right? Will give us, now this is the general view, okay, of this general question. Will give us all polynomials. But all polynomials, obviously all polynomials of degree n, or maybe I should just say not n, but so far what we have done, the polynomials you get might be of degree less than equal to n also. Do you guys agree with that? In the interpolation also, just because n plus 1 points are given and so on, it doesn't mean the polynomial will get value of degree n. So maybe I should have corrected. You can get a degree less than n polynomial also. Is that fine? Yeah, the sum of the PIs can be 0. And so who, yeah. And I don't know. So you have to see. Maybe they don't have to be 0, but they can cancel out and so on, right? So the degrees are not just n, but less than equal to n. Why this set less than equal to n is good? Because you see, this set is closed under addition. If you add two polynomials of degree less than equal to n, they are less than equal to n. But if you add two polynomials of degree n, they are not degree n necessarily, right? So that is why this is the right set. This is like a lower set. I mean, rather lower closed set, right? And if something is there, then things below it also there. So there is a something. So there is a, you know, so it's closed in that way, that sense. All right. So which set of n plus 1 polynomials will give us all polynomials? It's a question. But let's say that there is a set of n polynomials which do give us all polynomials. Then maybe we can try to prove that they give it to us in a unique way. That can be a good question, right? Assume that there is this collection of polynomials p1, p2, p3 till pn plus 1, such that any, so I'm not writing x anymore, right? Such that any p can be written using them, right? So the coefficients will obviously depend on p, obviously, but yeah. And now we're not interested in finding the coefficients, right? We're not interested in a pattern and so on, but we're trying to prove some general things, and this will imply things for what we have done also. Maybe I should start it with n, should start it with 0. That's better. Zero, 0. So can you say that these CIs will be unique? So assume that this is possible, but now we want to say that the CIs are unique. Show these CIs. When it is possible, maybe we will not answer, but CIs are unique. We will answer that into some, I mean, we'll just get an equivalent condition. There's no such thing as answering. Can answer. Yeah, can we show that these CIs are unique, or are they unique? Let's think about that. So far, the CIs have been unique. So this is not some out of the blue thing, right? So basically, then if in that case, it has to be done in a unique way. If you take 3 vectors and try to span all vectors in R3 using them by combination, then you can only do it in a unique way. If you take 4 vectors and span, then it's not unique. But 3 vectors, you don't have much liberty. Let's see. I mean, let's see if this is easy. I don't know. We'll have to see. But at least to some extent, we should be able to say. Right. So let's see. Let's think about this for homework, okay? Because I just want to give a little bit of view on this also. Maybe we can try to think. See, if you want to get all polynomials of degree less than or equal to n using these n polynomials, what are the first n or n plus 1 polynomials that you should get? Well, obviously the x to the power i's, right? That's the theoretical. I mean, that's the, so now we're just doing a little theoretical part, right? But you understand, right? Getting all the n polynomials is basically, right, like getting the x to the power i's first, right? So it's like, and that's it. When you get them, then you can get everything. Do you agree? Right? So that is really the key. So maybe we can writing it in a matrix language. Okay. P naught and V1 and so on should be possible. Ci should exist. Yeah. We are answering the first question. Okay. So we are kind of saying if there is a set of polynomials which has this property, which gives all polynomials, then let's see what we can say. And then maybe we can say the reverse also from there. Okay. This is just I'm trying. Okay. This is whether this can be said in elementary, we'll have to see. And then again, right? And in this way, x to the power n, and this is a must, right? This is an equivalent condition, right? Yeah, it's an equivalent condition. So no doubt whether you can get all polynomials or you can get these x to the power i's, it's an equivalent, these are equivalent statements. Right? So you can see, right? So what is basically happening is you are taking these, you are able to write these, and this is where you see the language of matrices comes in useful. And you have this huge matrix C, right? And using them, you are, is that right? Using them, you are writing. Yeah. And you see, you, right? You have this thing. Okay. So basically this system, so one way to say it is that I want to say that I want to say something that this determinant should be non-zero, but how can I say it? Just a minute. Right? So see, certainly, I mean, writing these all polynomials with degree less than equal to n using n+1, these n+1 polynomials is the same question as this this system of equations having solutions, right? This is the same question. And from what I want to say from here is that this implies that this matrix C is invertible. Yeah, I mean, see, if this matrix I mean, not clear what question I'm trying to ask. That is a problem. So if you have these n+1 polynomials, so the question really is, when will they give you all? Yeah, so I'm mixing up two things here. Yeah, so the question is, when will they give you all polynomials? Yeah, so if they give you all polynomials, then you should be able to do this. And in that case, yeah, but the question is what? Like, when will they give you all polynomials? Yeah, so maybe we can, just a minute. So yeah, so basically the question is, when will this equation have a solution? Right. No, but then what is really, yeah, right. So if this matrix is invertible, yeah, let me say it like this. Yeah, if this matrix is invertible, if this matrix is invertible, if C is invertible, right? If C is invertible, then you see, in that case, so basically if C is invertible, right, then let's look at C inverse. Then basically the C inverse X, right? When you do the C inverse X, where this is the X, right? Then what do you get? You get a row of polynomials, right? Like in this case, we're representing by these P naughts, right? But if you have an invertible matrix C, let's call it C inverse, not C, but C inverse, then the C inverse X will give you a collection of n plus 1 polynomials, right? And you are sure that those polynomials will always give you everything. Why? Because you can take the inverse of the C inverse. And then those polynomials will generate these powers of X, and so they will generate everything. Right. Okay. So whenever you're looking at an invertible matrix, so whenever you have an invertible matrix and you multiply that invertible matrix with these, right? And then you get this, then whatever polynomials you get, that should be, that those polynomials will give you everything. Okay. And so basically, if you now want to, but let me not go into that. The converse is also true, but I think that we get, yeah. Yeah. So let's not go into that. I think that's fine. This is okay till here. Okay. Yeah. So that's the thing. We did some solve basics, and then we also did some. Yeah. So if there are any questions, then ask me. Otherwise, yeah, let's not go further. Okay. Okay, then is it okay? Stop. Yeah. Okay. Thank you. Thank you. Bye.